So the learning goals for this week is to become familiar with different types of pumps. Because there are many ways that you can run a pump, so we have to look at quite a few of them. We're going to become familiar with different types of couplings, which is the connection between the motor, which is running the pump, and the pump itself. We're going to become familiar with the design of the tank, the reservoir, where we keep the hydraulic fluid, and become familiar with filtration in general, so filters and how we're going to keep the hydraulic fluid clean enough. And in particular, we're going to look at return and intake filters. We're going to look at more filters next week because we don't have time to do all of them this week. So we'll start off with looking a bit more at the pumps. So in last lecture, we talked about efficiency and the characteristic curves of pumps. So other design features that we have to keep in mind when we are designing a system with pumps is how are we going to mount the pump to our system. So are we going to bolt it to a frame, or does it need to be bolted to something else? Do we have to create something to keep the pump in place where it's supposed to be, close enough to the motor that the coupling reaches it and everything? So that's something we need to look at. We also need to look at the operating temperatures, because different pump designs have different operating temperatures, which will be highly important for our system. So we need to know what is going to be the operating temperatures that we are going to get in our systems. Noise level is also very important. If you're going to place this in the same room where people are going to work, it is nice to keep the noise level fairly low, preferably, if you can, beneath 85 decibels, because in a work situation, at least here in Norway, the law says that if you have it above 85 decibels in noise level, constant in your work environment, you're supposed to have protection for your ears. So if it's going to be inside a room, in a workshop, for example, where there are going to be mechanics or technicians working for an 8-hour day, you don't want this one running and making a lot of noise so that everyone has to keep their ears covered and protected. So it's either that or being able to place it in a different room so that you don't have people working in the same room. The hydraulic fluid that's going to be used. We looked a bit yesterday at these huge contraptions they used to lift the pipelines in the beginning of the lecture, where they were lifting it up when they were going to weld them together. And they were using seawater, basically, because they need so much water to pump into the system, because they have really large pistons. So they would have needed extremely large tanks of hydraulic fluid if they were going to use hydraulic oil for it. So then it was better for them to design it to use seawater and take that into consideration when they were going to set up the servicing intervals of them. But usually we try to stay with regular hydraulic fluids, which won't corrode everything inside. And then the type of pump will also be important for our design. And we're going to start looking at those in a little while, the different types of pumps. So we have quite a few basic pump types here. So we have constant displacement, where the amount of volume that you are moving for each rotation stays the same. So it's a constant volume. So you're constantly, as long as you're keeping the amount of revolutions, the RPMs, at a constant level, you will also be moving a constant volume through every minute. And then you have those which are variable displacement. So they are constructed in such a way that they can actually change the volume inside. So the volume that is pushing the fluid through the pump can actually change. So they can change the dimensions of the room where the hydraulic fluid is in while it's being moved through the pump. And then you also have more controlled versions of them. So some of the variable displacement ones will be they will react to the amount of pressure it has, so it will just sort of vary itself with regards to how much it's giving. But you can also have directly controlled ones where you can say that now I want this pump to pump a certain amount, have a certain amount of flow through it. So for hydraulic pumps, we have sort of a branching tree that we can look at for the different types. The first branch is for the constant displacement pumps. And those are usually gear pumps, so they are gears that are actually moving the fluid through them. And an external gear pump will look like this, where we have fluid coming in at the bottom, and it's being caught by the teeth, pulled around, and then sent out on the other side. And the same happens on this side. It's being caught by the teeth, pulled around, and goes out at the top. Then we have internal gear pumps. Here the fluid enters, and it gets caught either in this area or between these teeth, and then it's moved over to the other side where it exits. And up here, there is not enough room for the fluid, so all the fluid that's caught in here, it gets squeezed out and back into there. But you will, of course, have a very tiny amount of leakage coming through here and back. So you won't get, it's impossible to get 100% efficiency on that one, because there will always be a very tiny amount of fluid following all the way around. But most of the fluid will go through and out the other side. Annular gear pumps, we're not going to go into particulars on those. It's a kind of gear pump, but we won't look much at them. Screw pumps are a bit different. The ones we have looked at now, until now, have been placed on a shaft that's perpendicular to the flow. So the shaft has been going straight through the flow line, and then it's been rotating and pushing the flow as we go. The screw pumps are placed along the flow line instead. So here is the best animation I could find, which is not really a screw pump, but it is an Archimedes screw, which can be used to transport water from a lower area to a higher area. And it's the same principle that is in use in a screw pump. But usually you have two screws that connect to each other. We'll see a better image of it a bit later on when we look at screw pumps. The second branch goes down to constant displacement, varial displacement, or control pumps. So this can be any of the types. Here we have Vane pumps. They have a rotating disc in the middle, and then they have vanes or wings, you might call it, just like on a fan almost, that will extend. You can follow the red dot there, so it will extend as it goes through the bottom here. It will push the fluid through, and then as it goes to the top here, the disc is almost in contact with the casing, so that there's no room for fluid to pass over here. So the fluid passes in, gets caught by the vane, is pushed around underneath here, and then discharged on the other side. And there is, they can either be internally or externally pressurized. It was a bit difficult to find good ways of showing that in animations. We also have piston pumps. And those can be radial piston pumps, which operate almost in the same manner as the vane pump, only here we have an inlet on the top here. So these two black markers show where the hydraulic fluid enters the pump. And we have these pistons which are being pulled away, They are spring-loaded, so that they will always be pushed out of the rotating disc. But then as they come around on this side, there is less space between them and the casing, so they will be pushed back against the spring, and then these two black holes is where the hydraulic fluid escapes from the pump. So it just keeps on pulling in fluid into one of the pistons, and then the piston is pushed back, and the fluid escapes the pump. So in the Vane pump, the fluid was moved along the outer edge, while here it's moved on the inside instead. And you also have axial piston pumps. Here we have a shaft going through the pump, and then we have this plate which isn't horizontal, it's at an angle, so that as the shaft rotates, this angle is being rotated also, so that these pistons are being moved in and out as the shaft is rotating. We have hydraulic fluid coming in here. It gets through here and into a check valve, which will allow the fluid to go into the pressurized compartment, but not return back. So that it goes in here, it gets pressurized, and then it's pushed further on. And you see the combination of these two check valves makes it so that you can't get hydraulic fluid flow the other way around, so everything is blocked that way. We're going to look a bit more at the gear pump. So there will be space between the teeth here, and that's basically our displacement volume. So this is the amount of fluid that it's moving for each rotation between the teeth. And we'll have a pressure chamber. That is the part 2 here. And then we'll have the third, which is the suction chamber. This is where it sucks up the fluid. And only one of these wheels is connected to the motor. So the motor is running one of the wheels, and then the fact that these teeth are interlocking will run the other. So you only need to have one shaft be connected to the motor here, which saves up a lot of space. You don't, if that was not the case, you would have to have two motors, and you have to make sure that they were running at the exact same speed and everything. That would be very hard to do. So it's much easier to just run it on one. There, come back. And as the tooth leaves the gap in here, so the teeth will connect to each other, it will create a partial vacuum inside between these teeth, because they are basically in full contact with each other, these teeth, so that as one teeth is leaving, it will create a small vacuum in there. And the fluid gets caught inside here, and then it's moved along the housing all the way up. And then as the fluid gets into here, it will be forced by the tooth that is coming in here. It will force the fluid here to go into the flow. But at a certain point, this tooth will close off here, so that it will make it impossible for the hydraulic fluid to escape between the teeth there. And it will still be moving inwards here, so you would create a lot of pressure inside there, because you basically have incompressible fluid caught between two teeth there. So that is why they have this slot, which they have shown with just these hidden lines here. So on the back side here, there is actually more room, so that the back side of the teeth here are not touching the casing at all. So they actually have some room for the fluid to escape on the back side of this tooth, so it can just go behind it and up instead. Then you won't get the pressure problem in there. And this is the symbol that is usually used to show a pump, where you have the flow going from this side through the arrow, showing that it's being pumped out on this side, and you have a shaft that's going to be connected to the motor. Now you will have leakage in the gear pump, as I've already explained to you, and that is basically there will always be some fluid following through here, so that you don't get, you won't manage to push all of the fluid out here, so some will be following through. So that's one point of leakage. So that's the size of the gap between the housing, the tooth crests, and the sides. So there will always be, you can't have everything in constant contact, because then you would have a lot of friction, because you would drag steel against steel all the time, and that is not good. You will have very, very fine tolerances, so that there won't be much room, but there will always be some room. And in the gear overlap, as I mentioned just now, that some of the fluid will follow through. Was a question? If there is a cavitation problem inside. No, there would have been, you would have risked cavitation problems here if you didn't have this slot that sort of let the pressure out. So you could have risked a lot of problems in here if you didn't have that slot. So, but you will have a pressure drop here, and if you're running the pump too hard, at too high of an RPM, more than it's designed to handle, then you could risk cavitation there, because you are creating a slight vacuum inside there as the teeth are leaving each other. And then, of course, the viscosity of the fluid will have something to say for how much pump leakage you will have. So if the viscosity is too low, so that you have a too thin hydraulic fluid, you will get more leakage, because thinner fluid will manage to flow through smaller areas here. So you will have more fluid disappearing. And also the speed will have something to say. So if you're running at a fairly low speed, you won't get that much leakage, but as you increase the speed, you will get more and more leakage. And the volumetric efficiency indicates what you are actually getting, the effective flow rate, versus the theoretical flow rate. So in a theoretical flow rate, you would get 100% efficiency, but you are not getting 100%, you are getting 80 to 90% most likely. So that's the indication for it, looking at the efficiency. But you also have to remember that we have to have this leakage, or else we won't have any lubrication going on here, so that it would be difficult to operate it. And the suction can actually become larger than the pressure, because the flow velocity, we can put this on, the flow rate is equals to velocity multiplied with area, sectional area, flow velocity, volumetric flow rate, and cross-sectional area. And if the flow rate remains constant, but we are decreasing the cross-sectional area, then we will get a greater velocity. And that is basically what's happening here. We are getting a smaller area because we have the diameter on this side of the pump is larger than the diameter on this side. So we do, by increasing the velocity of the fluid, we are converting pressure energy into kinetic and heat energy. Then we get a pressure drop, and if we're not careful, we end up with cavitation. So we have to be careful about the velocities we have here. And that's what we saw earlier with the cavitation in the first lecture also, was that it was connected to the speed of the fluid. So the velocity of the fluid has something to say for it. So if you are creating a hydraulic system and you have a pump that's designed to be run at a range of 1,000 to 1,500 RPMs, it really won't be good to connect it to a motor that's running at 2,000 RPMs, because then you will have too much velocity in it and you will get cavitation inside. We're going to look a bit more at the different pump types. So we have the gear one that we've been looking at. For some reason they've switched around now, so it's going from the top to the bottom instead of from the bottom to the top, but it's still the same flow that is going along the housing and then out at the bottom. So an externally toothed gear pump, we usually have a speed range from 500 to 3,500 RPMs, and the displacement volume from 1.2 cubic centimeters to 250, so they can be pretty large, these pumps, but you can also get them very, very small. And a nominal pressure up to 160 bars, and with 80 to 90% approximately in efficiency, depending a bit on the pump and the combination of speed, displacement volume, and pressure in the system. Then we have the internally toothed gear pump. So you see it has the same speed range as the externally toothed. It usually has a bit larger minimum volume, and that has a bit to do with just the shape of it here. So you're getting teeth on both sides of this insert, so that you're getting a larger area or a larger volume being pushed around. It's more difficult to create a very small pump of that one. And it usually can handle a higher pressure. So if you want a higher pressure, you'll go for an internally toothed instead of an externally toothed. Can any of you, or does any of you dare to attempt to explain why the internally toothed one can handle a higher pressure than the externally toothed one? Anyone that can answer it? Or just attempt to answer it. Doesn't, if your answer is wrong, that doesn't matter, really. It's allowed to speculate. The thing is, if you look at these cutaway sections, so here you have two teeth being connected. So in the middle here, there is contact between the walls of two of the teeth. They're pushing at each other. So you have just the contact of two teeth. But if you look here, you have actually quite a few teeth that are in contact with each other on the internal and the external ring. So here you can get 3, 4, maybe even 5 teeth that are in contact with each other, which means that you have a much larger area to sort of place your forces on. So you have much more contact between your two materials here, which means that you can handle a much greater load than what you do here, where if you get too much pressure in here, your teeth will break off, basically, because it's just one teeth on another teeth, and another tooth. And here you have several, so that you have a more contact, and it can handle more strain. But these gear pumps also have an efficiency of 80 to 90%. And here you see a screw pump, as they are usually designed, where you have one shaft that's connected to the motor and rotating, and then you have another shaft that's not connected to a motor, it's just connected to the spiral teeth on the other one. So these are basically threads, much like in a lathe or a milling machine, what you use to move the tool around in order to get a precise location when you're going to cut into your material. It's usually these kind of threads that are being used to move them. They can also handle quite a lot of load on them. You'll be looking at these when you're looking at gears with Torbjørn in the theory lectures in mechanical design. So those are the screw pumps. The basics here is that the fluid comes in on one side, and the only contact between these two shafts is right here at the middle, So all of the area between the threads here can be filled up with fluid and will be, just like an Archimedes screw, will be transported over to the other side where it can exit. And these can usually handle a bit more speed than the gear pumps, and they can have quite large displacement volumes, but they can also be very small. And they can handle mid-range pressures, but as you can see, they can also handle very low pressures. So it's good to use if you're not going to have a very high pressure system. But the efficiency is a bit lower, 70 to 84%. Then we have the Vane pumps. They have, in general, a higher speed that they need. They need a higher rotational speed. They can handle less top speed than the previous pumps, but they have to have a higher minimum speed in order to work properly. And fairly small displacement volumes, but not that large ones either. So these are usually small pumps. And you have a fair enough pressure range, 100 to 160. But you can actually get efficiency up to 93% on them, so they can have really good efficiencies. Then we have the piston pumps, axial piston pumps. And here you can get a whole range of different solutions. So from very low speeds to 3,000, and then from 750 to 3,000. And it will give you a couple of different combinations of displacement, volume, and pressure. And efficiencies also. And then we have the radial piston pump with the same rotational speed range as the Vane pump. And basically the same displacement volume, but it handles higher pressure. And it's usually around 90% efficient. So if we're looking at speed, we want a screw pump. That's the best alternative if we need to have as high a speed range as possible. If we're looking at displacement volume, an axial piston pump is what's going to give us the best, most value for our money. And if we're looking at pressure ranges, it's both of the piston pipes can give us quite good pressure ranges. And efficiency-wise, it's the Vane pump that's going to give us the best. So if we look at these three lower ones, there are very many movable parts in those. So there's a lot that can go wrong. Doing a service assignment on one of these will require a lot of dismantling and then reassembling, exchanging parts that are worn that you need to exchange with new ones. Maybe you have to sort of grind a bit on some of the parts. You will have to do a lot of work when you're servicing them. While the three top ones have very few movable parts, and this means that we can get away with very quick services for these, because basically for the gear pumps you have two gears that are moving. Same with this one, you have an outer ring and the inner gear. And the same here, you have two shafts that are rotating. That's basically all we have of movable parts. So in the three lower ones, you will have many vanes or many pistons in each rotation, so that there's a lot to do there. Now we've looked at pumps and pressure relief valves. So we're going to look a bit more at couplings, which is the connection between the motor and the pump. And the mission of the coupling is to transmit torque from the motor to the pump. And it's also to cushion the fluctuations in the motor towards the pump and Vice versa, it's supposed to cushion pressure peaks in the pump towards the motor so that they won't affect each other that much. And it's also supposed to compensate if there is a shaft misalignment between the motor and the pump, so that when they have been mounted, the shafts aren't completely in line. That can actually be compensated by the coupling itself, so that you get sort of fix it. They can even be one of them can be slightly at an angle compared to the other one, and you can still manage to fix it with a coupling. And there are many types of couplings. Usually you can have something like this, where they have two joints. Each joint is connected to one shaft, so you would have one side connected to the motor shaft, the other side connected to the pump shaft. And then in between these, you have some sort of elastic component, an elastic plastic, or maybe even a rubber component that you actually use, so that they will rotate against each other, but they have this elastic part between them, which allows them to sort of cushion each other, so that you can get a jerk from the pump if it suddenly hits a pressure peak. You can get a jerk from the pump, and that's going to be cushioned towards the engine, so that the motor won't get the same jerk. Another way of doing it is to have each of the axles with a flange on, and then you can easily dismantle and assemble a coupling in there. So you just lift it into place, and then the entire center of the coupling here is a rubber tube, basically. You can have fully steel couplings. Then they are using teeth instead of direct bolting to transmit the power. So you will have a ring of teeth on the motor shaft. You will have a ring of teeth on the pump shaft, and then you have an external ring of teeth which are placing on top of this, so that the teeth from the motor are connected to the coupling ring, and the coupling ring is connected to, or the teeth on the coupling ring are connected to the teeth on the pump shaft. This enables it to handle the misalignment and stuff, but it doesn't really have much of a cushioning effect when you have steel on steel, so you won't get the same effect as the rubberized couplings there. And there are several different ways of creating these, but all of them use a central ring outside going on top of both of the shafts. Then you have the ones that are similar to these, but they are using claws, steel claws from each of the shafts. They grip into contact inside the rubber. So it looks, on the outside it looks like this one, but on the inside it's more. You can see this one has 3 steel claws, and they go into contact with the rubber ring, and then you have opposite 3 claws on the other side, and they also go into contact with the rubber ring, which has basically 6 claws then, so that it has room for 3 plus 3 claws. And you have different types of them, where you also have a rubber ring outside there again, so that you have 3 sets of rubber that can cushion. So if you have a system which is very susceptible to pressure peaks or fluctuations from the motor, then you can use several chains of rubber components, so that you get cushioning in several spots. So that was the coupling. We'll start looking at the tank before we do a break. So the tank is the reservoir where we keep all of the hydraulic fluid that's not currently passing through our system. So it's used for storage of hydraulic fluid. It is also used for heat dissipation, so that if we let parts of fluid that has just passed through the system and become heated by the system, if we let it just wait a bit in the tank before we suck it up again, so that we have enough fluid that we don't need to use the fluid that has just passed through the system. It will get a chance to dissipate its heat into the rest of the fluid in the tank, and then into the walls of the tank and out into the environment. Which is often why they put the return parts into the tank as far away from the suction part as they can, because then the fluid has to travel through the entire tank before it's sucked back into the system by the pump. It is also supposed to allow the fluid to separate air, water, and solids out from it. So if you have a large tank, and you're getting fluid in from this side, and you are pumping out fluid on this side, there will be circulation in this tank, in the fluid. But if we first look at any solids, for example, that has been metal particles from the different moving components inside the system that has been released into the fluid, follows the fluid out, ends up here, and the solids are, of course, heavier than the oil, so they are going to gather up in the bottom of the tank, and they're not going to be sucked up by the pump. And when it comes to air, or we'll look at water first, because water will end up with the same. Water is, at least if we're using an oil-based hydraulic fluid, the water will be heavier than the oil, so it will also end up at the bottom of the tank, not being sucked up by the pump. And air bubbles that have been formed, they will have a chance to bubble up and disappear from the fluid at the surface. So this gives us a chance to remove quite a lot of contaminants from the hydraulic fluid. But of course, in order to make this a very effective system, you will need to have a very large tank in order to do this. It needs a large area, both in the bottom and on the top, in order to separate everything. So that's why we also use filters usually, because you really don't have room to do all of this. So you do the best that you can with the room you have available, and then you supply filters later on to help remove contaminants. The tank itself usually acts as the structural base for both the pump and the motor running the pump, and even other hydraulic components. So often the tank will have a very rigid steel frame where you can connect and mount all of the other components on it. So you get a very compact system by doing this. The system we have in our lab doesn't have this. It has the tank on top of the table and the pump is below the table, if you remember it from the image I showed last lecture. But still, usually it's everything very close by each other. So it's usually mounted to the tank, if you can. We'll look a bit at this one. Not sure if it's the projector that doesn't like showing stuff, or if it's the system itself. So we'll look at this tank from the textbook. So we have the motor and pump on top here. So they have been mounted directly to the top of the tank. And we have the suction tube on this side, and it's going fairly deep into the fluid, so that it gets to, even though the fluid level might drop, we have a leak somewhere, we can lose quite a lot of fluid before it starts becoming a problem. And if you have many large pistons in your system, and all of them are being extended, then you might end up using quite a lot of the fluid, so that if all of the pistons stay extended for a while, you will have quite a low fluid level for that moment, because much of the fluid is trapped inside the pistons, pushing them out. But as soon as you pull the pistons back again, you're going to fill up the tank with the fluid. This side is, of course, the suction chamber inside the tank. And the suction chamber is usually compartmentalized from the rest of the tank by a moderating plate. So it has tiny holes in it, which allows the hydraulic fluid to pass through. But it also makes sure that there's not a high flow rate from this side and to the other side, so that the fluid here gets to stay fairly quiet, so that particles and water can sink to the bottom and air can escape out of the top of them. So we'll do a 15-minute break now, and then we'll continue afterwards. Right, so we've looked at the suction side of the tank right now, and we'll continue on. So this is the main return chamber. And this is where the hydraulic fluid is returned into the tank. And this is also where it sort of rests until it has been able to get the water and air and particles out of it. As you can see here, it has a sloped bottom, this tank. That is so that everything that gets down to the bottom here of water and particles and stuff, it will end up down by the drain screw. So that when you're doing checks here to see how much water you've had in your system, how much water has been divided up from the hydraulic fluid, you can actually open the drain screw, and then the first thing that will happen is that you will probably get a stream of fairly clear water coming out, and then hydraulic fluid is going to start getting mixed into the water, and then you can close the drain screw again, because then you have drained most of the water that was in the bottom of the tank. So it's a very quick way of getting rid of water in your hydraulic fluid. And you have a level indicator, which is usually just a clear plastic or glass, just a small window where you can actually see the hydraulic fluid within. So if you can't see anything in the minimum fill level, then you have too little fluid in there, so you have to fill some fluid in. There is a filling filter, so that if you're going to fill hydraulic fluid in here, it's actually going to go through a filter before it enters the tank. And then all the way at the top, you have a maximum fill level indicator. So it's the same principle as the low one, where you can actually look in, so that if you're going to fill fluid into a tank like this, like we talked about before the break, maybe you have lots of very large pistons that are being run through this tank. It would be wise to put everything, as much of the fluid as you can, into the system. So extend all pistons and get as much fluid into the system as you can, so that you are at your minimum level here. Check if it's below your minimum fill level. If it is below, you're going to have to fill until you at least can see some liquid in the level indicator. And then you do the opposite. So you retract all of your pistons, you pull everything in, you get as much fluid as you can back into your tank, and then you can check if it's up by the maximum, because you don't want it to be beyond the maximum fill level. So if this small window up here is completely filled with liquid, so that you can't really see through it, you only see the hydraulic fluid, then you have a bit too much fluid in your system. So it would be wise to open the drain screw and just tap out some of it, so that you won't get pressure inside your tank. And at the top, there is a vent with an air filter, which is needed because you will have air being sucked in once the fluid level drops, because a lot of fluid is being sucked into the system. Then you will, of course, need to get air in here, else you'll be creating a vacuum above the fluid. And also, if the opposite happens, much of the fluid that's in the system is returned to the tank, it's getting filled up again, then you need to let the trapped air escape, or else you're going to create air under pressure in there. You don't want that in there. And that's why it has a filter on it also, because you want to avoid pulling in dust particles that will mix with your fluid. And then we have the return pipe. So this is where all of the fluid that's been through the system returns and gets deposited down here. So we're going to look a bit more at the tank. And we're going to look at a couple of guidelines for designing a tank, because even though when you are creating a hydraulic system, you will often use a lot of components that you will just buy from different suppliers. So the pump you will buy from someone who specializes in pumps, All of the valves will be bought from a specialized company and all of that, but the tank is often something that you'll have to think about designing yourself. Because especially if you need a tank that's specially designed for your purpose, maybe it has to fit into a certain compartment in your system, so that it has to be specially made, custom made to fit. So that will be something that you fix yourself then. So first of all, we'll have to think about the size of the tank if we're going to design it. And the size is dependent on the pump delivery rate, so how quickly is how large of a flow rate is the pump delivering. It's quite annoying that it goes black every now and then. You also have to think about the heat generation in the system and the maximum temperature of the fluid. Because if you have a lot of heat generation and the maximum fluid temperature is fairly low, then you will need a large tank in order to have much heat dissipation. Either that, or you're going to have to place a cooler on it, so that you actually, before it's returned into the tank, it runs through a cooler, so that it's being cooled before it returns. We'll look more at coolers later on. And you also have to look at the maximum volume difference that you need, basically the difference between the maximum and the minimum fluid level in your tank. That will have something to say for the size of your tank. And of course, as I mentioned to begin with, the location of the tank. If you have a spot, a corner where you're supposed to put it in, but it's not a 90-degree corner, maybe it's at an angle, probably maybe 60-degree angle or something, then you're going to have to create a triangular tank which is 60 degrees. And that's going to be a custom-made tank. You won't find that one in a supplier's brochure or anything. And then, of course, the circulating time. So how much time do you need from the fluid being returned into the tank before it gets sucked back into the pump? So the size of the tank will have something to say there, because you will have a sort of a minimum distance that it will have to travel and a minimum speed that it will have to have. So then you have to look at this, just how much time do you need from return to inlet again. So just to make sure that you have enough time, both for dissipating the heat that has been generated and for getting the water and air out of it. And the shape of the tank, of course, has something to say. As I said, if you have a triangular tank, because that's where you have room to put it, that will have a lot to say for the design. And also where in your system the suction and return lines are coming from. So if you're getting a suction line in this triangular tank of yours, you have the suction line has to be all the way into the corner, and then your return line is way out towards the opening, then that will be okay. You can just let the return go down in as far away from the suction as you can put it. But if both of them come out of the system at approximately the same place, you're either going to have to try to manipulate the system in order to get them apart from each other, or you'll have to do hoses and stuff to just move their locations a bit. So that will have something to say for the design of the tank. And of course the baffling and moderating plates that you set up in order to halt the flow of fluid from the return chamber into the suction chamber. So you're trying to keep this liquid as calm as possible as long as you can before it's sucked to the plate and into the suction pipe. So some systems might need actually several layers of these plates to sort of get enough circulation time. And then also the bottom plate. As you can see in this one, you need to have an inclined plate in the bottom. That is something that you really want, just to make it easier to tap tap water from the bottom of the tank. So you'll have to look at how that is also going to be done in your design. And of course, venting with the air filter. So where on your tank can you place this air vent where you have room enough to have a filter above it. Then we've gotten to the filter section. So we're going to start looking at filters. I think I've forgotten some stuff here, but so hydraulic fluid contamination, we'll look at that first. It's the initial contamination, first of all, so it's the contamination that's already in the fluid as it comes to you from the supplier and when you fill it into your hydraulic tank, because most likely there will be some contamination. You have very, very, very clean hydraulic fluids that come, but they are very expensive also, so you might want to buy a cheaper hydraulic fluid if you can. So you will have the initial contamination anyway, which could be, if it's a lot of hydraulic fluid you're going to buy, it might actually be cheaper to have a filtration system to run it through before you fill it into your tank, because then you can buy a cheaper hydraulic fluid which has more contaminants in it, and then you can filter it yourself before you put it into your system. And then there's the contamination that happens during the operation of the system. So this is the steel particles from movable parts, dirt that will enter the system. Because even though you have, for an example, in a piston, a cylinder with a piston, so we're going to there is usually some sort of scraper ring that's placed here, which goes around the shaft of the piston, so that when the piston is retracted into the cylinder, it's going to scrape dirt from the shaft of the piston. But it's not going to manage to scrape all the dirt from it. So that some of the dirt will actually manage to cling to it and then end up inside the fluid. So you can get that kind of contamination also, especially like in a large truck or something that's moving around in maybe in an open pit mine, where you have a lot of dust floating around. It gets trapped on the shaft. The shaft has a thin film of hydraulic fluid on it. Since it's constantly being pushed in and out of the cylinder, it's going to constantly get hydraulic fluid on it. And some of it, a very thin layer, will always follow, be clinging to the shaft as it goes out of the cylinder. Dust will settle on that hydraulic fluid, and it will be pulled back in. So you will get contamination from this. Yeah, usually some kind of rubber type. And sometimes, depending on the pressure levels in here, you might have some sort of steel armoring inside the rubber, just to make it able to handle higher pressures. And the problems with contamination in the fluid is, for an example, if you have a valve that's going to close off the flow, so you need to have contact between this surface on the valve and the seat in order to close it completely. If you then get tiny particles stuck between these areas, then your valve won't close properly, and then you'll have leakage. You will have hydraulic fluid leaking past the valve. And the same if you have a piston. If you get too large particles ending up on the side of the piston, because the piston will always need to have some room so that it won't scrape along the edge all the time. So it will need to have some room here. And if the particles get too big, they can actually be trapped inside here along the side of the piston. And if they are then rotated so that they really get jammed in there, then you're going to create a lot of damage to the sides of the cylinder and also to the sides of the piston. So I've seen one example of this when I was working as a mechanic, and that looked really bad. So it looked like someone had taken it apart, and then they had been doing a sharp metal object and just scraping on the sides of it. So it looked horrible. That was because they had gotten too large particles into the system. So it can do a large amount of damage there. Yeah, this is just to show that this is the valve seat, this area here. And you have the contamination particles coming in. And here it is, the piston play, as it's called, which is the amount of room the piston has to move inside the cylinder. We also have this part, which I had forgotten to animate. The purpose of the filter is to filter the contamination to a permissible level, so that you keep either the size of the particles small enough, or that the amount of the particles is also small enough. So usually it's a combination of the two. So you filter out the larger particles, and you also filter some of the smaller particles, so that you keep the amount of smaller particles low. And this protects against wear and tear in the system. So as I said, with the cylinder and piston I looked at, where it just looked like someone had been scraping inside it, that's a lot of wear and tear, and this one didn't function properly. That's why we took it apart and looked at it. So we had to go in there with a lot of equipment and try to make it better. And selecting a filter that's based on the hydraulic components you have, because different hydraulic components will have different sensitivity to contamination. So a very, very small valve, it can't handle large particles at all. It needs to have a very good filter so that you have very small particles, or else it's going to be jammed. While a huge piston, so you have in the Heave compensation systems that they use on cranes on boats, which they use to compensate for the heave motion of the waves. They are like quickly a meter in diameter, these huge cylinders and pistons. There you often have quite a lot of piston play, so that you have room for larger particles. It's usually filtered well below what it can handle, though. But it's a component that can handle very large amounts of contamination. And the contamination particles are measured in micrometers. And then we look at the absolute degree of filtration, or we look at the nominal degree of filtration. So the absolute degree of filtration will be what we are actually filtrating, how much we are managing to filtrate. The nominal one will be basically the value that's given for the filter. So what the supplier says, that this filter can handle this much filtration. So that's when you're going for the nominal. We'll also look a bit at the mean pore size, which is the average size of holes in the filter, which allows fluid through it, because that will say something about the size of the particles that the filters let through. Because if the particle is larger than the pore in the filter, it's not going to pass through. It's just going to get stuck on the surface of the filter. Here we have a couple of pictures. Usually this is how they look. Most filters look something like this, where you have the sort of, looks kind of like paper or some kind of fabric almost, and then it's been folded like this, and that's to create as much surface area as you can. Because if you had just wrapped this material once around a cylinder, you would have the same surface area as the cylinder. But now when they are folding it like this, they are getting quite a lot more. You can usually multiply it with 10, 20, 30 to get the surface area of filtering fabric itself. So that's the whole point of doing this sort of folding of it and putting it in there. And they are usually cylindrical, so that you will have either the fluid entering through the center and then passing out through a sort of sieve, a metallic sieve that's blocking out the really large components, and then the really large particles, and then the rest will pass through the filtering, the folded and layered filter, so that it gets a lot of surface area to catch particles in. I've seen some of them where it's sort of submerged into the contaminated liquid, and then it sucks it out through the center. But then often this sieve part will be placed outside, so there will be a cylinder with holes in it outside the filter itself. So now we're going to look a bit, this is an oil filter for a car engine. We're going to look at how it's made, but it's the same concept that's used on hydraulic filters, and it gives you a good insight into how these look when you get to see how they are made also. So.
Changing your car's oil filter a couple of times a year is an easy way to prolong the life of your engine. The oil pump forces oil through the filter to the moving parts in the engine. The filter's job is to block dirt and metal debris from getting in between those parts and causing engine damage. They make many oil filter parts from steel coil, a sheet of steel on a roll. They start by unwinding the roll and feeding the coil into a press. The press contains a series of dies, each of which progressively stamps the steel into the shape of the specific part they're making. This press is churning out tapping plates, a component on the end of the oil filter that screws onto the car's engine. Hot off the press, the tapping plates travel on a magnetic conveyor to the welding station. There, a robotic arm loads them onto the welding carousel. But before any welding begins, a nozzle applies sealant around the rim of each plate. This will fill any gaps left between the parts after welding. A robot now welds the tapping plate to another steel part called the bottom ring. This ring will hold the gasket, the rubber seal that prevents oil from leaking out as it travels through the filter into the engine. The welded parts, known as the bottom assembly, now go into a machine that cuts a thread pattern through the center. This will enable the oil filter to be screwed on to the engine. Another press produces the oil filter steel body called the canister. The dies first stamp out a rough canister shape. Then they reduce the diameter and make the can taller. Finally, they cut off the excess. Elsewhere in the factory, another machine cuts and perforates pieces of tin-plated steel coil and rolls them into tubes. We'll see where those tubes go shortly. Yet another machine prepares the filter's key component, a filter paper that works like a fine sieve, trapping dirt, carbon, and soot. First, the machine pleats the paper so it will fit inside the canister. Next, the machine cuts the continuous ribbon of pleated paper into lengths. It folds each piece into a circle, fastening the ends with the steel clip. The next machine assembles what's called the filter cartridge. It places each filter paper over a tube. The tube's job is to reinforce the paper against the force of the oil pumping through it. This machine glues a capping disc on each end of the filter paper to hold the tube in place. A heater cures the glue. Now for the final assembly. As the canisters go by upside down, automated arms insert the filter cartridges. A worker then puts a thin rubber disc on top of each cartridge. This disc will prevent the oil from draining out of the filter. Now for those bottom assemblies we saw them making earlier. A worker positions one on each canister. Then a machine called a seamer folds its edge down, forming a rim, just like the rim of a soup can. Now the conveyor turns the filters right side up as they file by 5 nozzles spraying powder paint. An infrared oven dries the paint in about 90 seconds. Then a printing machine stamps on the product information. The conveyor now turns the filters upside down again as they travel to the gasket inserter. Its automated plungers insert a gasket into each bottom ring. These automotive oil filters are finally finished and ready to do the dirty work.
So it's pretty amazing to see how they. I wonder how many thousand filters pass through each of those workers during one day. It has to be quite a lot. So here you can see how the machines were actually folding the filter and putting it into place. You could also see the metallic perforated stuff that they call it, which acts just like the sieve you use in your kitchen when you're making food. In the case of these oil filters for car engines, you would see basically at the top part, one of the last things they put in there was, just do a slight drawing here. It was the part that was being stamped out all the way in the start, which was a circular plate that was placed on the top, and it had a hole in the center, and then it had several other holes going around. And the hole in the center is where the oil is, the contaminated oil goes in. So it goes in and ends up inside here, then it has to pass through the filter before it exits through the other holes. So then it goes back up again and exits through it. So it's a very, very effective way of filtering it. So you can send it in through the center and get it out through the sides of it. So other filters might have an entrance at the bottom and just an exit at the side or something. There are many ways that these are constructed. But if you want a filter which you can stand on the outside of your system and then you can just screw it in, this is usually the way it's solved, where you have a central entrance and then you have several exits around the periphery of it. The one thing we need to look at when we're looking at filters is the beta value. So for an example, a beta 50 will be that there are, a beta 50 equals 10, means that there are 10 times more particles that are larger than 50 millimeters, 50 micrometers in the inlet, so coming into the filter, than it is in the outlet, so it's coming out. So it's filtering away 10 times more of the particles. So if you have 100 particles, if you do a sample of your fluid and you can count 100 particles that are larger than 50 millimeters, you should have 1,000 particles in the inlet, so that it should be 10 times more there. And this construction which we have with the folding and everything to increase the surface area, it means that the filter will have a longer life also, because you have such a huge surface area to spread all of these tiny particles on, so that the the filter will still allow fluid through, even though it's been trapping hundreds of thousands of particles that are too large to pass through it. And of course, there is, if you go into the, almost the microscopic level here on the filter, you will see that you will have these pore sizes. They won't be exactly the same all over this paper stuff. So some of the pores will be larger than other pores. So some of the pores will let through particles that are larger than 50 micrometers, and that's why you are getting some particles larger than 50 micrometers in your fluid, but you are trapping 10 times more in the fluid. So this is just to show why we are looking at the mean pore size. It tells us a lot about how much we are going to block in the filter. So we're going to look a bit at a couple of filters here where we have an X value, which will be put in here in the beta. So if we have 1 to 2 micrometers in it, we will use a filter like this in a system that is highly sensitive to extremely fine contamination with calculable high reliability. So usually this is aviation applications and inside laboratories where you really can't have any contamination at all. In a laboratory, it will often mean that the equipment is very, very small. So since the equipment itself is very small, it can't handle very large particles of contamination in the fluid. And in aviation, it is mainly for security. You want as little as possible of contaminants in your plane. You don't want to fall down, so you want the plane to be as secure as possible. 2 to 5 micrometers is for sensitive systems with high performance control and regulating systems, and usually with high pressure in the system. This is also frequently in aviation, but also in robotics and machine tools. I'm pretty confident that for an ROV, the part of the hydraulic system that is closed off, that is only running the thrusters and internal hydraulics, often uses very finely filtrated fluid, because they don't want the thrusters to seize up while it's and not the manipulators either. They want those to be able to move very finely. So the manipulators are basically robotics because they are robotic arms. So 5 to 10 micrometers, then we're looking at high quality industrial hydraulic systems where you want to have a high level of operating reliability because you want it to work just like in the factory you just saw in the clip. You don't want one of the machines in the middle of the production line there to just go, I'm not working anymore because I have too much contamination in my hydraulic fluid. You want it to be operating reliably for as long as possible, and they usually have long service lives, so that they usually work for a long time because they have the very very good fluid, and they're also being looked after by the people that run the shop. So they have regular intervals where they shut it down and check it. 10 to 20 micrometers. So general hydraulic and mobile hydraulic systems, medium pressure and size. So for a small truck or something, it would usually use this in its system. 15 to 25 micrometers would be a heavy industry system operating with low pressures, but or that they have limited service life because they're going to get a lot of wear and tear on their components. And 20 to 40 micrometers, then you have to have a low pressure system, and you have to have, if you're running pistons or anything, you have to have large amounts of play in it. So it needs to have room for these particles to actually move inside the fluid without scraping, making a lot of wear and tear on the insides of the cylinders. So now we're going to look in specific at the return filter, which is one way of filtering it. And the return filter is usually installed on top of the tank, right by the return pipe. Yeah, and the return line goes through the return filter before it enters into the tank. And it's designed to withstand pressure peaks. And if it's not designed to withstand pressure peaks, so that it's not strong enough to handle a pressure peak, then it has a fast-reacting bypass valve, so that if you get a pressure peak, a valve beside the filter will open up and let the pressurized fluid pass through there until the pressure is normalized again, just so that you don't blow out the filtering paper in the filter. It's less expensive than high-pressure filtering because it's on the return side, so the return side of the system, it doesn't have any resistance, internal or external resistance. There's no movable parts, there's no pistons or anything, so the fluid is basically just flowing straight back into the tank. So there's not, the pressure is approximately zero on that side. And we have some important characteristic values for the return filter. So the operating pressure would be dependent on the design. Usually it's a maximum of 30 bars. So you usually have very low pressure on the return side. Some systems might have, if it's on a mobile hydraulic system, so for an example an excavator or something where it's running its pistons and stuff, they sometimes have completely closed off tanks so that they have no air vents or anything in the tank. So it's a completely contained unit. And that means that if you're getting a lot of fluid back, so you're retracting all of your pistons, a lot of the fluid is being sent back, then you're going to have an increased pressure in your tank. But then it's important that this increased pressure in your tank, which will also affect the return line, it can't be more than 30 bars, or else you're going to start ruining your filter. It can have fairly high flow rates, so up to 1,300 liters per minute if it's just a filter placed on top of here, and up to 3,900 liters per minute if it's a return line filter, so if it's placed inside the return pipe, because then you can stretch the filter over a larger area, so you can allow more fluid to pass through it. And the degree of filtration is usually 10 to 25 micrometers. So that's within the range of the mobile hydraulics of a truck or an excavator. And you have a permissible differential pressure up to roughly 70 bars, which is heavily dependent on what type of filter elements you have. So that would be described more closely in the data sheet for the exact filter that you're looking at. Then we're going to look a bit at intake filters, which is the opposite of the return. So this is a filter placed between the suction pipe and the pump. So it's forcing the fluid from the tank through a filter before it enters the pump. So usually it's placed inside the suction line somewhere. And it's used when your required cleanliness is not assured in the tank, so that when you can't be 100% sure that all of your, if you have a return filter also, that the contamination inside the tank, you can't be 100% sure that it's going to be below the level that's acceptable for your components. Then you will put in an intake filter, because then you need to assure that it's low enough once the liquid enters the pump. And this only protects the pump. So it's the pump that decides if the pump is very sensitive to contamination and you can't ensure a low enough degree of contamination just by the tank itself, that's when you need to put on an intake filter. But there is a disadvantage to this, because it's going to make it more difficult for the pump to pull in, to suck in the fluid. So that it's going to increase the internal resistance of the system, because the pump is working harder to manage to get the correct amount of fluid in. And this is due to a considerable pressure drop, because you get a pressure drop between the filter and the tank side of the filter and the pump side of the filter. So basically all of these pores in the filter, they act like tiny, tiny, tiny throttle points. So you want to be aware of this with regards to cavitation and stuff in them. Yeah, so if the filter is too fine, you quickly end up with cavitation. And these are usually equipped with a bypass valve because you don't want the filter, if the filter is clogged up, then you're going to destroy the pump if you just continue pumping. And it's not getting enough fluid through the filter, so it's getting too little fluid, it's getting too little lubrication, and then it's going to destroy the pump. So that, yeah?
When you say the filter being too fine, what exactly do you mean?
Yes, so the pore size of the filter, so it's not letting through larger particles. So if you have too fine of a filter, too small pores in the filter, it's going to block too much of the fluid flow through it. So it's still going to let the fluid pass through, but it takes a bit more time for it to pass through. And that's why they have these bypass valves, because then if there is too little fluid entering the suction pump, then you're going to create basically a vacuum between the pump and the filter, and that's going to open up the bypass valve so that you get the required amount of fluid to the pump so that you don't destroy the pump. And for these filters, you have a contamination indicator, and that's mandatory to have it. So you have to show, you have to be able to read how much contamination there is in the filter. So it's built into the filter itself that you can see how contaminated it is, so that you can exchange it in time. So that if, for an example, if you have a service interval that every 6 months you're going to exchange it, then suddenly after 4 months, when you're checking up on it, you're looking at the indicator, oops, this one is too contaminated now, so I have to change it now. I can't wait 2 more months for it. And we have some important characteristic values. Degree of filtration is usually 60 to 100 micrometers. And permissible differential pressure up to roughly 0.1 bar, because that will be the vacuum. So that's why you need the bypass valve. So if it gets more of a vacuum than 0.1 bar, then you have to let through more hydraulic fluid. And here's the symbol for an intake filter with a bypass, which means that you have the pump up here somewhere. So it's going through the filter, and if you get too low of a pressure up here, you're going to start pulling through here, because then you're compressing the spring enough. So you're basically sucking the ball up in the check valve. So then it's opening up and you get fluid through. And you also have the possibility of having switchable filters, which is very nice to have as if one of the filters gets choked up, then you can just switch to the other. So you're using one filter at a time. And if this one gets clogged up, you switch to this one for operation, and then you do maintenance on that one. And then once the maintenance is done, it's ready to be switched back if this one clogs up. So it's one of the ways that they keep production lines continuous and stuff, so that they can do service on them without actually stopping everything. So a very quick summary before we stop for today. We've looked at different types of pumps, and we've become familiar with different types of couplings. And we've looked at how tanks are designed. We've looked at filtration just in general. And then we've looked in specific at return and intake filters. And we'll look at several other filters next week, once we have our lecture then on Wednesday. There was actually 2 pages of references for this one, I think. And also at the end of this one, which will be available sometime during the weekend, there is a nice documentary. I haven't watched absolutely of it. I've just think I've watched 30 of the 45 minutes in it. So just like the one about the Troll platform, it might be nice to just look at this because it looks at machine hydraulics, so the use of hydraulics in large machinery. So it's nice to just get a view into how this is used, especially if you don't have much experience with hydraulic systems from before. So if you've worked with trucks and forklifts and stuff, so you've seen hydraulics in action, maybe it won't be all that exciting to watch this one. But if there are any of you that have absolutely no experience, I highly recommend watching this one. Yes, then we're done for today. You have a good weekend.